Welcome back to The Explainer. Today, we're taking everything we've learned about acoustics and neuroscience and boiling it down to the absolute essentials. We're zeroing in entirely on Section 7.4, the summary, to answer one massive overarching question. How do our ears and our brains actually code pitch? We've covered a ton of ground on the complex ways our ears process sound, but now it's time to distill all of that into the definitive key takeaways. We've got 6 key areas on our roadmap today: repetition and pitch range, coding pure tones, harmonics on the membrane, the power of resolved harmonics, pitch extraction models, and finally, the neural basis mystery. This flow will take us perfectly step by step from the known, measurable physics of the inner ear directly into the unsolved mysteries of the human brain. To really set the stage here, we have to acknowledge a thrilling reality about this field. When you listen to your favorite song, your ear is rapidly translating physical sound waves into electrical neural signals. And honestly, we know that part really well. We know exactly how periodicity is represented as a physical signal right there in the auditory nerve. But how your brain extracts that raw data to make you actually feel the pitch, that is still a massive scientific mystery. As the source text brilliantly puts it, we are at the stage where facts begin to be replaced by conjecture. It's a magnificent puzzle, and perceptual experiments on human listeners are what currently guide our search for these hidden neural mechanisms. All right, Section 1, repetition and pitch range. Think of periodic sounds. These are simply sounds with a waveform that repeats over time. When they repeat in a certain way, they're associated with a distinct musical pitch that perfectly corresponds to their repetition rate. But here is the critical limitation. Our brain only translates these repetitions into a true musical pitch within a very specific window. We're talking about a range from roughly 30 Hz on a low end up to about 5,000 Hz on the high end. To put that in perspective, if a sound repeats too slowly, say below 30 Hz, it just sounds like a rhythmic pulsing. Imagine the distinct, separate chops of a helicopter blade. It doesn't sound like a musical note, right? On the flip side, if it's too fast, well above 5,000 Hz, it loses that distinct musical quality and just sounds like a sharp, undefined hiss. So this 30 to 5,000 Hz sweet spot, that is the boundary where all of human music, melody, and recognizable pitch lives. Moving right along to Section 2, coding pure tones. When we strip away the complexity and look at the simplest sounds possible, we find 2 distinct neural coding mechanisms at play. First, there's the rate place code. This mechanism relies entirely on location and intensity. Specifically, it's the pattern of firing rates across neurons that are tuned to specific characteristic frequencies along the basilar membrane. Basically, it's a map of where the vibration is strongest. Then we have the temporal code. Now, this one is all about timing. Instead of just looking at where the neurons are firing, the temporal code relies on neurons firing in strict, phase-locked rhythm with the actual tone itself. The nerve impulses literally match the timing of the sound wave's frequency. So what's the verdict? Which one does the brain actually use to hear a pure tone? Is it the location code or the timing code? Well, the consensus in auditory neuroscience points heavily to the temporal code, the precise timing of those rhythmic neural spikes. Or potentially, the brain uses a clever team-up of both methods, combining the location of the active neurons with the precise rhythmic timing of their firing to reliably produce what you perceive as pitch. Okay, Section 3, harmonics on the membrane. Let's step up the complexity and see how complex tones physically behave inside the cochlea. There is a stark difference in how our nerve fibers react to different types of sound within a complex tone. For what we call resolved harmonics, the nerve fibers lock onto the fine, smooth sinusoidal waves of the vibration. They track the tiny, precise details. But for unresolved harmonics, the fibers behave very differently. They react to a much messier, broader envelope of interacting waveforms. They're essentially riding the larger, overarching wave rather than tracking the individual ripples. It all comes down to physical space on the basilar membrane. Lower harmonics are resolved. Think of them as clearly separated instruments in an orchestra. You've got the flute over here, the cello over there. They create distinct, separated vibrations that don't step on each other's toes. Because they're separated, your neurons can easily phase lock onto the clean individual frequencies. But the higher harmonics, those are unresolved. They cram into the exact same physical space on the membrane, crashing into each other and creating a complex, tangled waveform. Your neurons can't pick out the individual frequencies anymore, so they just adapt by riding the overall repeating envelope of that tangled mess. Which brings us to Section 4, the power of resolved harmonics. Get ready for an absolute mind bender of human hearing. You can completely delete the fundamental frequency, the core foundational pitch from a sound wave, and your brain will just fill in the blank. It's like an optical illusion, but for your ears. You'll still perceive a crystal clear pitch from the leftover harmonic clues. This tells us that our perception of pitch isn't just a direct one-to-one translation of the lowest frequency hitting our ear. It's an active, sophisticated calculation performed by the brain based on all the harmonic components present. And when it comes to the heavy lifting of that calculation, the resolved harmonics are the absolute stars of the show. They produce a much clearer, stronger sense of pitch than unresolved harmonics do. Whenever you're listening to a friend speaking in a crowded room or enjoying a guitar playing a rich chord, your brain is relying heavily on those clearly separated, resolved harmonics to figure out the exact pitch. They are the anchor points your auditory system uses to make sense of the complex sounds in our everyday environment. Now for Section 5, Pitch Extraction Models. So how does the brain actually pull this off? The first major theory is the pattern recognition model. Imagine your auditory system has a stencil. It takes the clear, clean frequencies of the resolved harmonics and tries to fit them into this template to guess what the missing fundamental pitch must be. It's a highly sophisticated pattern matcher. Awesome theory, right? Except, actually, it has one massive flaw. It completely fails to explain how we can still hear pitch when only the messy, unresolved harmonics are present. If there are no clean frequencies to fit into the stencil, the pattern recognition model completely breaks down. Yet, human listeners can still hear pitch in those situations. To fill that gap, we have temporal models. Instead of looking for a geometric pattern with a stencil, imagine the brain using a tiny, incredibly precise stopwatch. It looks directly at the time intervals between nerve fiber spikes. Because this rhythmic timing happens for both the clean, resolved harmonics and the messy, unresolved ones, this model accounts for everything. It essentially assumes the brain combines this timing activity across thousands of different nerve fibers, pulling all those tiny stopwatch readings together to estimate the fundamental period, which ultimately gives us the sensation of pitch, regardless of whether the harmonics are resolved or not. And finally, Section 6, the neural basis mystery. We've reached the ultimate scientific cliffhanger. We know the auditory nerve acts like a high-speed data cable, sending these incredible temporal and rate codes up to the central nervous system. But where is the central processor? Where exactly in the dark, complex folds of the brain does this raw data actually get transformed into the conscious sensation of a musical note? That is the million-dollar question. The leading hypothesis right now points toward the brainstem. The idea is that the brain acts almost like a funnel. It takes these incredibly complex, rapid-fire temporal patterns rushing in from the auditory nerve and converts them into a much simpler code based entirely on firing rate. Scientists suspect there might be highly specialized pitch neurons nestled right there in the brainstem that only fire or spike their firing rate when they detect a very specific periodicity in that incoming temporal data. But, and this is a big but, as the source explicitly summarizes, the evidence is inconclusive. Finding these elusive pitch neurons is literally like finding a microscopic needle in a haystack. It's an incredibly delicate task. We've seen tantalizing hints in animal neurophysiology, flashes of evidence suggesting we're looking in the right place, but no definitive proof just yet. But hey, that shouldn't be frustrating. It just means we're standing on the edge of a massive, wide-open frontier in neuroscience. Which leaves us with this final, provocative thought. We've meticulously mapped the physics of sound. We've decoded the electrical signals surging through the auditory nerve. But that final magical leap into human perception remains cloaked in mystery. As new, highly sophisticated perceptual experiments continue to map out exactly how we hear, guiding scientists ever deeper into our neural pathways, how close are we to finally discovering the exact hidden neural network that allows you to enjoy a simple melody? It's a profound question, and one that guarantees auditory science will be a thrilling endeavor for decades to come. Thanks for joining me on The Explainer, and keep questioning what you hear.